Hi, welcome to Keys Pre-Calculus. We are going to do a couple of examples from Lesson 3.5. The first one's in your book, the second one is not. But I wanted to work these so that you can understand what to do for your homework a little bit better. So let's look at example 2 on page 219. It says, in a research experiment, a population of fruit flies is increasing according to the law of exponential growth. After 2 days, there are 100 flies, and after 4 days, there are 300 flies. How many flies will there be after 5 days? This is most definitely an exponential growth problem. So if you look on page 217 in your book, you will see that the exponential growth model is y equals a times the natural base b to the x. You have learned this exponential growth model before. You learned it last year as y equals a times the natural base r to the x. It really doesn't matter which letter you choose to put in front of your x, which coefficient you choose to put in front of your x. It means the same thing. Now in this problem, it says that after 2 days there are 100 flies, and after 4 days there are 300 flies. So we can determine that our independent variable, the x variable, would be the time, and the dependent variable would be the number of flies. So our y would be the number of flies, and our x would be the time. So we could create two different equations with the information we're given. We know that 100 flies were produced after 2 days, so that would be 100 equals a e to the b times 2. And we know that 300 flies were produced after 4 days. So that would be 300 equals a e b times 4. Now what we don't know are our variables a and b, but we can use what we have to figure those out. Let's use our first equation to solve for a. So basically let's just isolate a. If I were to divide both sides by e raised to the b over 2, I would get a equals 100 divided by e to the 2b. I'm just going to switch those around so I can have my coefficient in front of the b. Now that I know that, I can substitute 100 over e to the 2b into the second equation for the variable a. So I would get 300 equals, instead of a, I would replace it with 100 over e to the 2b, and then multiply that by e to the 4b. Now, here I can do some cross-canceling. So, e to the 4b divided by e to the 2b, I could just subtract that, and I would get e to the 2b on the numerator. So my new equation would be 300 equals 100 times e to the 2b. I want to get rid of the 100, so I'm going to divide both sides by 100. And I get 3 equals e to the 2b. Now I still want to isolate the b, but it's an exponent. So the only way I can get rid of it now, or not get rid of it, but to simplify it, is to take the natural log of both sides, because I have the natural base e. So I'll take the natural log of 3 equals the natural log of e to the 2b, which is the same thing as saying the natural log of 3 equals 2b. Now I want to divide both sides by 2, and I get half natural log of 3 is equal to b. I can go back and substitute that in for this equation right here, a equals 100 over e to the 2b. So I would get a equals 100 over e to the 2 times b, which is 1/2 natural log of 3. I can simplify that by canceling out, oops, the 2, goodness, I can't get my pen to work, and the 1/2. They cancel each other. And I'm left with A equals 100 over E to the natural log of 3. So now I know what my B is, and now I know what my A is. These numbers aren't horribly practical, so when I plug them into my calculator, I get A as approximately 33.33, and I get B as approximately 0.5493. So now I can use these numbers to plug into my original equation of an exponential growth model and solve for when how many fruit flies will be present when the time is 5 days. Okay, I've moved my screen down a little bit so I'll have some more room. So actually, I can use any days to find out any number of fruit flies if I plug it in, if I make my new equation to be y equals 33.33 for A times E, and then 0.5493 for B, and then an X. To solve this particular problem, I will put a 5 in place of X, and then on my calculator, I will plug it all in and figure out that Y equals 520 flies. So after 5 days, I get 520 flies. Now, your problems number 23 and 27 work similarly to this one. And I believe I assigned both of those to you for homework. Now we're going to look at an exponential decay model. It's not in your book, so I went ahead and typed it up here for you to see. Radioactive iodine is a byproduct of some types of nuclear reactors. Its half-life is 59 days. That is, after 59 days, a given amount of radioactive iodine will have decayed to half the original amount. Suppose a contained nuclear accident occurs and gives off an initial amount of C of radioactive iodine. Write an exponential decay model for the amount of radioactive iodine present at any time t following the accident for part A, and for part B it says how long will it take for the radioactive iodine to decay to 20% of the original amount. Radioactive decay problems, or half-life problems, are exponential decay functions. So we're going to look on page 217 at our exponential decay model, which is equal to y equals a times e to the negative b times x. Remember, when we have a negative coefficient for our x, this makes this a decay model. This is the same thing as saying 1 over the base raised to an exponent. But in this case, we're going to use our negative coefficients to make it a decay model. So because our original amount is C, and we want to know what the half-life of C is, or half of C is after a certain amount of time, any given time, we're going to look for half of C. Well, half of C is going to be C, which is our A, times the natural base, raised to the negative b, times, in this case, it's 59, because we know our half-life is 59. Okay, the first thing I'm going to do is cancel out my c's. I can divide both sides by c and they go away. And I'm left with 1/2 equals e to the negative b times 59. And I can simplify that. I can get the b out of the exponent by taking the natural log of both sides, because I've got a base of the natural base. So I get natural log of 1/2 is equivalent to the natural log of, I'm going to write it as negative 59b. Well, the natural log, e to the 59b. So natural log of e, they cancel each other out, and I'm left with just natural log of 1/2 equals negative 59b. Now I'm going to get rid of the negative by multiplying both sides by -1. So I have negative natural log of 1/2 equals positive 59b. And because this is a -1 times the natural log, by properties of logarithms, by the power property of logarithms, I can take what I'm taking the natural log of and raise it to that -1. N equals 59b. Now, if I take 1/2 and raise it to the -1, that's the same thing as saying natural log of 2 equals 59b. So if I'm solving for b, I get b equals the natural log of 2 divided by 59. And when I type that into my calculator, I get b is approximately 117/10,000. So if I take that number and put it into my exponential decay model, then I can get the an equation that will tell me the amount of radioactive iodine present at any time t following the accident. So that's going to be y equals, instead of a, I'm going to put c, because c is the original amount of iodine, times e raised to the -b, which is going to be -0.0117 times time. That gives me my general equation that I can use in Part B. Part B says how long will it take for the radioactive iodine to decay to 20% of the original amount. So I don't know what my t is. I need to solve for it. So I'm going to use the equation, my general equation, y equals c times e to the -117/10,000 times t. And I will be solving for t when my y is 20% of the original amount. So what does that look like? Well, that would be 20% of my original amount, which would be 0.2, times c, equals c times e to the -0.0117 t. And I'm solving for t. Now the first thing I can do is cancel my c's, because if I divide both sides by c, they go away. So I'm left with 2/10 equals e to the -0.0117 t. So to solve for t, I take the natural log of both sides, so natural log of 0.2, or 2/10, equals the natural log of e raised to that power, which gives me just -0.0117 times t. And now I'm going to solve by dividing both sides by -117/10,000. So when I do that, I get t equals natural log of 0.2 divided by -0.0117. And when I type that in on my calculator, I get approximately 138 days. So it takes 138 days for this radioactive iodine to decrease to 20% of its original amount. Now your problem number, I believe it's 19. Yes, 19 is going to be worked in a similar way. I wanted to go through these couple of examples with you to show you basically how to solve some of these models. The rest of them should be fairly straightforward. Enjoy doing your homework.